Google DeepMind developed an AI using neural networks to defeat the topmost player in the game of Go, which was
That
considered almost
was a
impossible.
great achievement of AI. So do any of you have an idea about the game of Go?
Yes.
Yes, ma'am.
So Go is actually an extremely difficult game. The state space is huge, and it was thought to be a really difficult game. While AI systems have been adept at playing chess for quite some time, Go was supposed to be a very difficult game for AI to crack. However, as you mentioned in 2016, this company called DeepMind, which was acquired by Google, they used deep reinforcement learning to beat the world champion at that time, Lee Sedol, at that time, and that put a sensation. And then there have been different incarnations of that algorithms, AlphaGo, AlphaZero, etc., which can self-learn and using deep RL have been able to achieve a very difficult task. Any other example, one or two examples, some of you like to talk about?
Ma'am, self-driving cars.
Self-driving cars is another thing which have intrigued us a lot. So we do have autonomous driving, self-driving cars.
Like Amazon uses, yes, I'm Ritavan, sorry. Amazon uses image, neural networks for computer vision and all to separate, what do you call it? Unusable products, like defective products from usable products.
Right. So, all these companies, they use a lot of AI, yes, to sort products. Actually, another very important, aspect that Amazon uses is robots for picking objects in their huge warehouses. So that has impacted, their operations greatly. So Google uses AI to cool their data centers and so on. So just one more.
Medical applications.
Yeah.
In the medical application, to see the effectiveness of tumor, means it is harmful or not.
Medical applications, AI has made a huge impact.
Ma'am, in smartphones, we have a technology of facial recognition, and that is also based on AI.
Yes. So let us go to medical applications. Nowadays, AI can replace radiologists in detecting, chest X-rays, and annotating chest X-rays. Then in detecting breast cancer, AI systems are said to be more effective than humans in diabetic retinopathy and many domains in the medical world. What was the other thing that you mentioned?
Face recognition.
Face recognition. Actually, face recognition, AI is very good at face recognition, but this is a very controversial technology because that has a huge impact on privacy. So there are a lot of debates around this. But what we can understand that AI is extremely powerful. And in the age of COVID, a lot of the fast pace of development of vaccines, trying to find medicines, etc., have been fueled by different AI topics. Okay, but while there are a lot of there are places where the AI achievements have been phenomenal and have impacted how we look at it, there are also different risks associated with AI. And there are different concerns, some of which we will talk about later in this class and maybe in this course. But for example, one of the concerns is the energy consumption by the huge AI models. For example, in natural language processing, OpenAI developed GPT-3, which is a huge deep learning model containing as many as 175 billion parameters. And running these models have, the energy consumption have a significant, impact on the planet. Then there are various concerns about privacy. For example, when you say face recognition, that is people think that is a huge infringement on privacy. And AI algorithms, especially machine learning algorithms that are trained on data, they inherit the bias which is there in the data. And then there are issues of fairness and a lot of many different things which are associated with AI. So let us try to look at what we mean by AI. So what is the definition of artificial intelligence? So I will like you to suggest some definition of AI.
Like a very simple definition would be a machine which behaves like a human.
A machine, that is one way of looking at AI. So humans, we believe, have natural intelligence, and a machine that behaves like human, we can say that it has artificial intelligence. That is one way of defining AI. So any other definitions? Any other?
Ma'am, machine which can think can call all AI.
Machine which can think?
Yes, ma'am.
Yeah, so another definition is machine which can think, because thoughts and thinking is something that we ascribe to intelligence and human beings. So if we look at machines which can think, that is one way of defining intelligence. Again, there are different ways of defining AI, which have slightly different connotations, and we can discuss. Yeah, that is one second definition. Anyone else would like to define? So we have got machines which act like humans, machines which can think.
Yeah, it is a way to simulate a human brain into a machine and understand how human brain works.
Right. So that is something like, a combination of these two definitions. A machine which can think in the way humans think and act in the way humans act.
Ma'am,
Yeah.
is it a machine that can take decisions without being explicitly programmed to take those?
Right. So the machine can come up with the intelligence on its own without being told exactly what to do. Right. So these are some definitions, and we'll look at some. These are just two of the definitions. One picked from American Association of AI, the another I picked from MIT Technology Review. So, for example, the quest to build machines that can reason, learn, and act intelligently. Then the first one, the scientific understanding of mechanisms underlying thought and intelligent behavior and their embodiment in machines. Now, how these two definitions differ from the definitions that you gave, these definitions do not necessarily talk about being like humans. Rather, they're talking about behaving intelligently. So one can define intelligence as something which mimics the intelligent beings that we know in the planet, namely ourselves, or we can define intelligence on its own, but it is very difficult to define what we mean by thinking and what we mean by intelligence. Now, there are different ways in which different fields have approached AI, different viewpoints through the lens of which you can view AI. So from the engineering viewpoint, it is about getting machines to do many useful things. For example, understand language, translate, recognize people, etc. From the cognitive science viewpoint, which is about trying to understand about human brain works, it is a way to understand how natural minds and mental phenomena work. From the philosophical perspective, it is a way to explore certain basic and very interesting philosophical questions. Now, I will come to 4 dimensions in which AI is defined by Stuart Russell and Peter Norvig in their book, The AI, A Modern Approach. So the AIMA book. So here they have put a matrix of different ways in which people have defined AI. So one of this is to think like people. This is the cognitive science or neuroscience approach, as some of you have told. Then it could be, forget about what the machine is thinking. Whether the machine can think is a debatable question, but what we care about, whether machines are acting like humans act. And then there are other dimensions. For example, a machine that thinks rationally. Now, thinking rationally is not synonymous with thinking like a human. So human beings may be rational, may be irrational. So when you say thinking rationally, you can give some objective definition of what a machine is supposed to do. And the fourth dimension is the machine that acts rationally. You do not care about what the machine is thinking, whether the machine can think, but you look at whether the actions that the machine can take are based on some optimization principle. So is it optimizing something? And that is the perspective in which many of the topics in the course will focus on that. Even though there are other ways in which we can look at AI, and there have been studies in all this domain. So thinking rationally, for example, has a long tradition dating back to Aristotle. So when you look at, what is logical thought, how do you represent, how do you infer, etc. But many people think that it is also important to look at how machines act, even though there are certain controversies. So if you have a neural network where, which behaves reactively and the thinking process is not apparent, but the machine is able to perform optimally, it may be what you are looking for. Or you may be very interested to know what is the thought process and explanation behind what the machine is doing. Now, we will look into a brief history of how artificial intelligence came into being. So let us talk about John Turing. So John Turing published a landmark paper in 1950 called Computing Machines and Intelligence. In this paper, he asked the question, can machine think? Now, this is a very difficult question to answer. So Turing came up with an operational definition of how to evaluate this. And for this, he came up with an imitation game, which is also known as the Turing test. Now, so instead of evaluating thinking per se, the way in which he formulated is a problem is whether a machine can imitate a human being during a conversation with another human. This is a test of whether the machine could think. So in this setup, C is a judge, and inside the room, there may be a human being B, or there may be a computer A, or an artificial intelligent system A. Now, the human judge can ask questions to the being who is inside the room and get the answers. Based on these responses, the judge has to decipher whether the entity inside the room is a person or a computer. So it was told that if a computer can pass the Turing test, then we can say that that computer is intelligent. So, Turing test, whether the test itself is relevant or important is not really relevant, but this was a first actionable definition of the question to evaluate how machines think. Next, we come to the event when this term artificial intelligence was coined. In 1956, John McCarthy, he organized a conference at Dartmouth College. This was called the Dartmouth Conference, where the big scientific minds in this field, they attended this conference and they spent the summer. During this workshop, the term artificial intelligence was introduced, and to unify the various research efforts which were taking place at that time on automata theory and cybernetics, information processing. So to give the machines the ability to think. And these are some of the people who attended the conference, John McCarthy, Marvin Minsky, Claude Shannon, Ray Solomonoff, Alan Newell and Herbert Simon, Arthur Samuel, Selfridge, Rochester, Moore, they were great scientists of that time. And they formulated different proposals and they thought about what intelligent machines can do. For example, one of the propositions that they made is that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. So this was also during the time when the computers have just come into being, and there was a huge enthusiasm of what you could have computers to compute, and there was a great optimism that one could achieve intelligence by using a computer, by programming a computer. And a lot of optimism was there. These are some of the quotes from some of the scientists in this domain. For example, Herbert Simon, who later, along with Alan Newell, went on to win the Nobel Prize in Economics. So Simon made this comment that machines will be capable within 20 years of doing any work that a man can do. Then Minsky in 1970 said from 3 to 8 years we'll have a machine with the general intelligence of an average human being. So in those days, as a fallout and many of the work involving the people who were involved in this Dartmouth conference, a lot of early successes were there, a lot of optimism was there. The first machine learning system was developed by Arthur Samuel. It was a system that could play chess at the level of advanced amateur. Then Newell and Simon developed the logic theorist, which could independently prove a theorem. The theorem was already known, but they came up with a very elegant proof of the theorem. They then went on to formulate the general problem solver. Then there was the geometry engine, which was developed by Gelantner, etc. So a lot of optimism was there, a lot of systems were developed. So during this period, from 1950 to 1970, there was a great enthusiasm and optimism about AI. So what you should understand that AI, or the perception around AI, I'm not saying the field has seen steady progress, but the perception around AI and the funding of AI research, it has gone through different ups and downs. So in the first few years till 1974, there was a lot of optimism, a lot of different systems were developed, which became very significant in the early days of the computer. In parallel, there was development in the field of neural network, which we will talk about separately. But then what happened is that because the people were so optimistic, they did not have a good understanding about the limitations and of the computing and other paradigms, and a good understanding about the computer science algorithms and in the complexity of the tasks. So this period of optimism was followed by disappointment. So there is this story which says that US defense had given a lot of funding for developing machine translation system. In those days of the Cold War, there was a lot of interest in developing machine translation system to Russia. So the story goes that when the evaluators came, this sentence was given to the machine to translate. The spirit is willing, but the flesh is weak, which was translated to Russian and then back to English using the machine translation system. And what came out was the vodka is good, but the meat is rotten. Actually, a very smart translation, but it did not amuse the people who had funded machine translation research. So the ALPAC report recognized the limitations of the technology, and actually the first AI systems, while they were very enthusiastic, they could not really scale up. And the reason was at that time, the computer systems were very simplistic. They did not have a lot of power. And then there was not a very good understanding of computational problems which are hard. So the way these problems were formulated, the search space grew exponentially. So because of the limitations in computations, the limited knowledge available to the system, the complexity of the problems, these systems could not scale up to real world tasks. And because of this disappointment, there was a withdrawal of funding into AI research, and this is said to be the first AI winter. Also, in the United Kingdom in 1974, the Lighthill report was published, which criticized the failure of AI to achieve the grandiose objectives which it had set out for itself. So Lighthill made this comment in his 1974 report. In no part of the field have the discoveries made so far produced the major impact that was promised. During this time, a famous computer scientist called Karp, they also came up with a set of problems, which in computer science people call NP-complete problems, which showed that there are class of problems of, the solution, the known solution of which are not computationally feasible because of combinatorial explosion. And so this sort of, people were trying to attack problems with not enough resources, with algorithms which did not scale up, and with unrealistic expectations. And this led to the decline, the loss of enthusiasm in AI research. During a similar time, for the connectionist domain, Minsky and Papert published a book called Perceptron, which pointed out certain limitations of one-layer neural network, which also contributed to the lack of enthusiasm in AI and a drop in AI funding. People also realized that there are certain, certain tasks which human beings find hard. For example, playing a game of chess or playing checkers, things that involve computation and number chunking, where the systems were good. But there are a lot of very, things, a lot of tasks that human beings perform effortlessly. A child picks up in the first, few years of his or her life, such as acquiring natural language, understanding natural language, being able to see the world and understand the world, being able to navigate one's way through the world. So these tasks which come very easily to humans, the systems were not, it was found difficult to have, develop systems that were good in this task. So in 1970s and 80s, there was a resurgent, interest in AI as the AI industry boomed. And this boom in the AI industry was led by knowledge-based systems. So this was the age of expert systems, where in different specific domains, the expert knowledge was encoded into rules, which could then the system could be run to automatically apply those rules and solve different problems. During this time, expert systems were implemented, such as the dendral system, which could infer molecular structure from mass spectrometry. Then the Mycene system in the medical domain, which could diagnose blood infections and recommend antibiotics. Then the XCOM, which could convert customer order into part specification, symbolics, and so on. So various expert systems were developed. So they simulated the decision-making ability of human experts to solve narrow specific problems. So, however, eventually these expert systems proved to be too expensive to maintain and difficult to update because they relied on getting human experts and encoding their knowledge manually. And this effort could not be sustainable, and they could not go beyond specific domains. They could not learn, and therefore they were not robust in handling rare inputs or unusual inputs which came. Now, during this time also, the desk, in the AI journey, So some special purpose languages were developed, namely one of those languages which was very popular was the Lisp language. And there were specialized machines which could operate on the Lisp language, and these were expensive machines. And during this time, the desktop computers also came into being. And because of their, the low cost, etc., they overtook this expensive Lisp machines, and the AI industry, the AI hardware industry collapsed. And also, as I said, that these expert systems which used expert knowledge and also they used deterministic rules. These deterministic rules, like if-then rules, they were not rich enough to capture the different nuances of the world, the uncertainties, etc. They required a lot of manual effort to maintain. And again, the hype in AI, there was a downfall. So this led to a collapse in the AI industry and what we call the second AI winter. Now, before we go to the next phase of AI, let us look at, there are different paradigms of AI. So what we have been talking about is the symbolic paradigm of AI based on logic and mathematics. For example, based on the thoughts of Aristotle and its logical thinking. Then there are two other paradigms which have been very important, especially in recent times, though their history is very old. The one is the neural or the connectionist paradigm, and the third is the statistical or classical machine learning based paradigm. So if you look at neural network history, actually neural networks, the first artificial neural networks were proposed in 1943 by a neuroscientist called McCulloch and a logician called Pitts. And then there was some progress theoretically on this sort of neural systems. For example, in 1949, Hebb gave a learning rule in order to update these neural networks or find the parameters of these neural networks. Then in 1958, Rosenblatt created the perceptron learning algorithm to train a neural network, which was a single layer of neuron. And there was some sensationalism around it. So this picture on the right is an implementation of the perceptron in the Mark-1 perceptron machine. And this machine could recognize an image with a 20 by 20 pixel camera and was the first implementation of a neural network system. So while there was a lot of enthusiasm during this time, something happened which killed neural network research. And this was the publication of this book called Perceptron in 1969 by two scientists, very knowledgeable scientists called Marvin Minsky and Seymour Papert. So this is actually a very good book. It did a lot of mathematical analysis. It also showed certain limitations. It showed that linear models, for example, a single layer of neuron, could not solve a simple problem which we call the XOR problem. The XOR problem is a simple problem. It finds out if two inputs are similar or not. So even though it's a simple problem, it turns out that this problem cannot be solved by a one-layer neural network. It does not mean that it cannot be solved, but this, it appears that this conclusion led people to lose faith in neural networks and killed the neural network research. And then, of course, after the so-called AI winter, there was a revival of connectionism. For example, in 1980, the neurocognitron was developed by Fukushima, which is the first version of convolution neural network for images. In 1986, the backpropagation algorithm was reinvented for training multi-layer networks. In 1989, there was a first, large-scale application of neural network by Jan LeCun, where the US postal system adopted the system for digit recognition to recognize the PIN codes in the envelopes. So in the 1990s onwards, there was also a boom in the statistical approach. Again, this was nothing new. These work had been done by statisticians earlier, but there was a resurgence of probability. There was also focus on uncertainty. And there was a general increase in technical depth, the agents and learning systems, etc. And during this time, the field of deep learning also took off. So deep learning is nothing but neural networks with a large number of layers. While initially when backpropagation algorithm came into being, because of the limitations of computing power and the way the algorithm worked, it was difficult to train deep networks. But several methods were devised during that time. For example, layer-wise pre-training, etc. Then deep convolutional network like AlexNet, was a sensation when it in the ImageNet competition for object recognition, this system beat the conventional computer vision system. And as one of you have told in 2016, these are just some glimpses. The AlphaGo system was able to defeat the world champion in the very complex game of Go. Actually, AI has borrowed from many different fields. For example, some of the ideas in machine learning and other domains of AI came from early days. For example, linear regression was formulated in 1801, linear classification in 1936, uniform cost search, on basis of which you have this heuristic search, etc. It was formulated by Dijkstra in 1956. Markov decision process, which is a very important concept for stochastic representation of stochastic state spaces, reinforcement learning, etc. This was proposed by Bellman in 1957. Now, in the 1980s onwards, as I said, there was a big advance in statistical machine learning, and some of the important concepts which was developed during that time was the Bayesian network by Judea Pearl, then support vector machine by Vapnik and Cortes, and so on. This slide, which I have borrowed from that by Peter Stone at Texas Austin. On the left, we see the reality of scientific progress in AI, while on the right, we see the perception around AI, which shows how the perception of society about the importance of AI has gone through ups and downs. And today we are going through an up cycle, whether it will sustain, and we do not know. Now, let us come back and step back and talk about what we mean. I said that one of the ways to define AI is to think about a system which can behave rationally or which can make rational decisions. So what is it? What does being rational mean? So rational means to achieve predefined goals. So rationality does not always focus on the reasoning process, but in sometimes it only concerns how good the decisions are. And one of the ways to evaluate rationality is to look at the utility of the outcome. So one of the ways that Russell defines rationality is the system should behave so as to maximize the expected utility based on the knowledge which is available to the system. So taking advantage of the prior knowledge, the current knowledge as obtained by the perceptions, etc., the machine should be able to act so as to maximize the notion of expected utility, which depends on the performance measure that you define for the system. Now, an agent can be defined as one which works with an environment. The agent senses the environment or observes the environment through its sensors, through the input that it receives, and the agent can take actions which in turn can affect the environment. Now, how the agent takes the action, there are different ways in which it can do. And how do you judge whether the agent can take effective actions? That also depends on what is the measure by which you are going to evaluate the system, or the performance measure. What is the prior knowledge of the environment or background knowledge of the world that the agent has? What are the actions that are available to the agent, and what the agent has observed till date from the environment? Now, this picture is taken from the Pac-Man environment from the AIMA book and the Berkeley course. So this is a computer game called the Pac-Man. So where you are moving a system, moving an agent which can go north, south, east, and west. And in the game, you have different points. So you want to win the game quickly. So there's a penalty associated with each step. So there's -1 per step. +10 if the agent can find food and rejuvenate itself. +500 if the agent wins. -500 if the agent dies without winning. +200 if the agent is able to kill the ghost, and so on. So this is a toy system, computer games. So the environment is the dynamics of the Pac-Man and the ghost. So there are two agents, one which you can control, the other is the ghost which you cannot control but can observe. The actions available to the agent is to go north, south, east, and west. And the sensors, the agent can see the entire state space. A second agent that we will talk about is an automated taxi. It's a taxi driver agent. So how do you measure the performance of the taxi driver? So what is the income, whether the customer is satisfied, what are the costs of maintaining the vehicle, fines, etc. In these terms, you can define the performance measure of the taxi driver. What is the environment? The taxi driver has to operate in the city streets where there are other traffics, pedestrians, traffic lights, etc. Then what are the actions available? The steering, the brake, the fuel. What are the sensors available? Camera, radar, accelerometer, engine sensors, and so on. Right? So if you have to have a self-driving taxi, that these are certain things which are available to the agent. The agent has a goal, and the agent has to decide how to drive. So in the AIMA book, they characterize an agent. In order to be able to specify an agent, they say there are 4 aspects that you have to define. And this is known as PEAS, or P's. P stands for performance measure, E for the environment, A for the actuators, and S for the sensors. And the environment can be of various types. For example, the Pac-Man environment is fully visible, whether the taxi environment is partially visible. In the Pac-Man environment, there are multiple agents, the agent and the ghost. In the taxi also, there are multiple agents like the other vehicles, other pedestrians. Pac-Man is a deterministic environment, taxi is a stochastic environment. This environment can be static or dynamic, discrete or continuous, and so on. Now, we will talk about 3 pillars on which the field stands. And this is as defined by Parsi Liang, who is currently at Stanford. So artificial intelligence, there are 3 pillars of AI. 1 is modeling, 2 is inference or reasoning, and 3 is learning. And let us define what we understand by this. Modeling takes a real-world problem with all its complexities and formulates them into a mathematical objects, into an abstraction which we call model. And model should be such that we can analyze the model and come up with algorithms to solve the model. So modeling is the task of going from a real-world task to a formal task. So for example, suppose you want to navigate your way. You have to go from one source place to a destination place. And there are a lot of complexities. There is the traffic, there are the different roads, their characteristics, their surfaces, a lot of things. But when we want to find the shortest path or the cheapest path from one place to another, you may try to abstract out the important parts of it and define it as a graph, connecting the different places. So from the real world, you come to a model, which is an abstract definition of the problem, for which you can find a solution in the abstract space, and that solution can be interpreted into a ground solution. As Rodney Brooks has said in '91, Rodney Brooks had a lot of contribution in robotics, the SOAR architecture, etc. So Brooks has mentioned that the process of abstraction is the essence of intelligence and the hard part of problem being solved. So along with abstraction, another aspect is very important. This is the way of representation. Depending on the way you represent the problem, this impacts the efficiency with which you can solve problems. Also, when you come up with a representation, if you take into account all the knowledge that you have, the background knowledge and other knowledge, which is relevant for solving the problem, that will impact how well you can solve the problem. Now, the second pillar of AI is inference. So given a model, the task of inference is to answer questions with respect to the model. For example, given the map and the roads, etc., you could ask the question, what is the shortest path to go from point A to point B? Suppose you want to go from Kharagpur to Bardwan. So what are the ways in which you can go? What is the distance? What is the route which has the shortest distance? What is the route which will take the shortest time? What is the route which will take the shortest cost if you can travel by public transport and so on? For example, in Google Map, you have something like this implemented. You can give a source, you can give destination, and you can find out the different paths and the cost associated, or at least the time and the distance associated with them. So the focus of inference is on efficient algorithms that can answer these questions. So we separate what we want to compute, this is called modeling, and how we compute through algorithms, which are the inference algorithms. But, so this is an example. You have a model and you have the inference algorithm, which will come up with the shortest path for this particular problem. So the third pillar of AI is learning. Where do you get the models? In certain cases, the real world is so rich. So if you have to build a faithful model, you cannot write down all the aspects of the model manually. So that is where learning comes into being. The idea behind machine learning is to learn the model from data. Instead of constructing the model, one of the ways to do it is that you construct a class of model or a skeleton of a model which has certain parameters, and from the data and the experience, you find the values of these parameters. So this paradigm of learning allows us to learn the models, and it also, by depending on the learning algorithms, this comes as a bridge between the logical tradition of AI and the statistical tradition of AI. So this is an example of learning. There's a model. The model, you don't have the parameters. Based on the data, you learn the parameters. Now, if we look at classical AI, the declarative paradigm of intelligence, these are some of the steps. The environment, the agent senses the environment, gets the perceptions. From this, the agent comes up with a model. From the model, it comes up with a plan about how to act, and then actually takes the actions. Now, models are of various types. These are some of the topics that you will study in this course. There are state-based models. For example, for search problems that we will study as the next topic, these search problems, we have the models where you are operating in an environment where there is no uncertainty, and you know what actions take you from one state to another state. Then you also have state-based models in adversarial games. In adversarial games, you are not the only agent. There is another agent which you do not have control on that agent's action. You can control your actions, but everything is deterministic. And the third framework of state-based model is Markov decision process, where there is some stochasticity involved, where there is some randomness in nature, which is captured through probability distributions. And then there are variable-based models. For example, when you study constraint satisfaction, we will look at variables and the values that they can take. For example, take the game of Sudoku. In Sudoku, you have to come up with values such that each row, each column, and each 3x3 sub-block has the digits 1 to 9. Now, if you want to fill up the cells in Sudoku, you can get a much more efficient representation if you take into account variables. So the key observation is that the order in which you fill the squares do not matter, but the evaluation is critical. So you can have variables and you can try to assign values, and you can come up with an efficient representation of this. A second example is Bayesian networks. In Bayesian networks, there are also variable-based models where you have random variables which are dependent on each other, but these dependencies are soft dependencies, and these can be expressed by conditional probability tables. The details of these domains we will study in this course. Then another paradigm of AI is logic, where we talk about representation and inference. Suppose you want to represent these knowledges or these facts. The rice harvest is good, but there is not enough water. If there is a lot of rain or not a lot of sun, then there is enough water. And you want to find whether you can infer that there is not a lot of sun. If you want to work with this, you have to way of representing these facts. And you can represent these facts as propositions, and you can use rules of inference to find out what sort of inferences sound. Then there are other facts for which you cannot express easily by propositional logic. For example, consider these facts. Someone from Kharagpur stole the crown. An honest person does steal. All smart people are honest. And the question is everyone at Kharagpur smart? If you want to reason with such cases, so you can use some formalism such as first order logic, which has variables, which has predicates, constants, and different types of quantifiers like existential quantifiers, universal quantifiers, and so on. Again, these are things that you will study in details later. And then we come at the paradigm of learning, where the simplest case, you have a data, and from that data you learn the model, which involves inductive generalization. So unlike logic, where you have certain sound rules, so that given some facts, you can come up with some definite inferences, learning involves generalization, which is not always logically valid unless you incorporate certain bias. So it requires a leap of faith. Now, with this basic exposition of the different topics of AI, let us again come back to a summary of what is intelligent. So we can say intelligence is the ability to perceive and act in the world. You should be able to represent knowledge, reason with knowledge, behave intelligently, and then interact and apply. So there have been a lot of advances in AI and AI optimism. Will not go into the details, and many technical progresses. I've just listed a few of the technical progresses in AI today. So today, AI systems are very good at generating new objects. So these powerful generative systems can compose text, compose audio, compose images of sufficiently high standard. So it is very difficult to distinguish between what is real and what is synthesized or fake. So you have all these deep fakes. For example, the CEO of NVIDIA gave a speech, and few people could realize that the entire person, lip movement, speech was generated by the computer. Then in natural language processing, there has been a tremendous progress and very swift progress in different aspects of NLP, which has beat all the benchmarks in NLP. Earlier, the different computer vision systems that were applied on the ImageNet, they, in a few years, they could, they could better human performance. Then there's a lot of applications of machine learning in healthcare and biology. We talked about DeepMind in the context of AlphaGo. So DeepMind released AlphaFold, which applied deep learning technique to make significant breakthrough in a very complex biology challenge of protein folding. Scientists use machine learning models to learn representations of chemical molecules, which could be used for effective chemical synthesis planning, and so on. But many people perceive AI as a threat. For example, the famous Elon Musk described AI as summoning the demon. And people have been, the law philosophers and other people have been talking about the risks of this technology. For example, Nick Bostrom, said that AI is a technology that threatens humanity in general. And many people have made different comments. So there are many questions which we have to answer. So suppose you have an autonomous car and the car, there's an accident. Who is liable for the accident? Then people question, will machines surpass human intelligence? So people talk about singularity of technology. Would machines have conscious existence? Would they have rights? These are real problems which are being debated today. What is mind? How can a physical object have a mind? These are all philosophical questions. Can we build a mind, etc.? But there are some real causes of worry, like the bias. An AI system which learns from data inherits the bias from the data. AI, while it can be used for technologies that benefit mankind, society, and the planet, they can also be used for sophisticated weapons which can destroy or have an impact on the human race. Then we talked about the liability. What if a robot has an accident? Who is liable? Then people are afraid that AI will take away jobs, especially the low-end jobs. So with this, we stop the first part of the lecture. I'm sorry we do not have a lot of time, but I will be happy to take questions and discuss more. So if I can take 5 minutes from the next lecture or a few minutes, so I would like to know if you have any questions.
Ma'am, what are the general prerequisites for this course apart from the PDS course that we took in the first semester?
So there are certain things that we will need in order to understand. For example, understanding about programming is of course very essential, but some understanding about algorithms, etc., will be useful. Certain exposure to probability is useful. A little bit about statistics, optimization. So we will try to, give those background when we teach those topics.
Hello.
Today, it was a history, so I did not really go into the explanations of any of the topics that I talked about.
Ma'am?
Yeah.
Ma'am, what is AI?
Ma'am, you said that the artificial intelligence, the machine inherits the bias from the data, but this having this kind of bias is not always useful. So is there a way to like remove this bias from the data?
There is a lot of work people are doing to remove the bias. For example, so one of the biases, for example, is gender bias. So you take a machine translation system and you take a language. So there are certain languages. In English, you have two different pronouns, he and she. In another language, for example, in Bengali, there is only one third person pronoun. Now, it was observed that when you translate that, X is a cook, when you translate to English, you will get she is a cook. And then you translate he is a computer, he is a computer engineer, you translate to he is a computer engineer. This is just an example of a bias which comes from what is there in the data. So there are bias of gender, bias of race, etc. So if you are cognizant of the type of bias, then people are working on algorithms to remove that type of bias. And it impacts people in a very, very different ways. For example, if you're trying to get credit from the bank, if the system which decides who is, which person will be given credit, if it is based on data which is biased, based on personal biases of decision making taken by the bank people. So they may discriminate people from different localities, different racial backgrounds, and so on. So, if you want to find out whether, people are using face recognition and other type of technology to try to understand whether a person is likely to be a criminal. Now, it was found that the bias of those systems are tremendous. People have been recently been cognizant of this topic, and a lot of people are trying to understand. First of all, they have found that these AI systems have a lot of bias. In some cases, when you are aware of the bias, people are also, some researchers are trying to work on how that bias could be removed. But overall, this is something which is a very difficult task because we are also always not conscious of our biases. And the main thing about technology is it augments the bias. While the good things are being augmented, the bias is also multiplied when you put it into a system and it gets more and more. It's multiplicative effect.
Yes, ma'am. Thank you.
Yeah, Prathamesh, do you have a question?
Yes, ma'am. Can you hear me?
I cannot hear you. I also
Hello,
see.
ma'am.
Yeah, please.
Ma'am, what is the AI market in next decade or in coming years?
You will know about it more than I. So please do some research to find out the value of the AI market. So there are a lot of reports by Gartner and others, McKinsey, etc. So you can consult those. I'm not aware. I mean, I do not know the figures.
Excuse me, ma'am.
Yes.
Excuse me. Ma'am, you said that. Sorry, ma'am. Someone muted me. So, ma'am, I was saying that, ma'am, you said that we took the data and from the data the machine learned. But, ma'am, the data entry people, they are not very much educated. So, ma'am, how do we ensure the credibility of that data? And also, ma'am, moreover, ma'am, how much data is required for a particular problem?
These are, we cannot answer these questions as generalities. Yes, some of the data are entered manually. A lot of data is generated naturally. For example, in what you publish on the web, what you write in your email, what you converse, there are data which come from natural sources and which have their imperfections and, which is also characteristic of natural systems. Data come in different ways. Data has to be sanitized, curated, how much data for which problem, these are specific cases one has to reason about that. So today I will not answer these generalities, but when we look at specific topics in machine learning, either in this course and other courses, then those things can be discussed.
Okay, ma'am.
So Kirti, you have some question?
Yes, ma'am. Ma'am, in the matrix definition of AI, one of them was act like human. What exactly is meant by acting like human? Does it mean only the physical aspect, or does it include something else?
No, decision, so in this, for example, if you are, trying to play a game of chess, you try to emulate how a human expert plays chess.
Doesn't that, I'm sorry, ma'am, but doesn't that come under thinking like human?
Thinking and acting, you can act without, and you can, so acting may involve a lot of deliberation and thinking, or maybe, you do not care how the thinking is taking place, or you understand how the thinking taking place, you only do act. For example, groups and all, they define different architectures of AI. One is called the reflex architecture. In the reflex architecture, you act instantaneously without explicitly deliberating. For some of the neural network based systems are reflex architecture. So you have a neural network where you feed in a lot of things, immediately you take an action. So you do not pay an emphasis on the thinking process, but you look at what is the outcome. So these are two ways, two lenses through which you can view AI system. Whether you focus on how the reasoning has come into account, or how you look at what you act. In many cases, people were focusing, we don't care about what the AI system is thinking. We want to only see that the system is optimal. But nowadays, people are more and more focusing about what is the thinking process, what is the explanation, because as AI systems have become more powerful, you have to answer questions in the court of law. You have to, understand what the AI system is doing. So the thinking process has become more useful in today. So I think, there are a lot of questions. It will be nice if you can put those questions in the chat, and I will try to address them right now. But we are a little late, and I think Professor PPC will take the next class. So Macharla, Ritoban, please put your questions on the chat.
My question is quite elaborative. It will be really difficult to put it in the chat.
Okay, you write an email. We will take it some other class. Okay.
Okay.
But you can write the summary of the question so that we can bring it up in a later class.
Okay, ma'am.
PPC, will you like to take over?
Them 5 minutes break, I think. We should give them 5 minutes break before we
so let us take a break and then we will come back.
We'll start at 9:15. Take a break. We'll start at 9:15. In the meanwhile, they can put it in the chat box, and the recording can be stopped. Whosoever is organized the recording, please stop it. We'll restart it again when my class starts.